Hello everyone. In the previous lecture, we have been discussing the, about the dihedral group, okay, or rather towards the end of the previous lecture, we were discussing about the dihedral groups. So this is an interesting family of groups. By that I mean, for each positive integer n, you end up getting a group d2n. You end up getting a group of order 2n. Okay, so you can do so for each positive integer n, but for some reason we will only focus on the integers n greater or equal to 3. Just let me have a quick look. Yeah, even okay, it makes sense for n equal to 1. I just want to be sure. As you can see, uh, okay, so there could be certain rooms for confusion. So let me first highlight that. Okay, but this is customary to go with the symbols. Okay, so here you get to see this element r and you get to see this element n. Sorry, get to see this element s, but you uh, yeah, but you, I mean, so when you just get to see r and when you just see these two letters r and s, you, when you just see r and s, you do not know what is n. For example, whether n is n or whether n is m or n is 10 or n is 20 and so on. Okay, so while discussing this group, when you know that we are discussing about the dihedral group d2n, okay, then then we know that r and s, I mean, then this is implicitly understood that r and s are precisely these two elements. Okay, so for s there is no room for confusion. Okay, at least the way we have introduced s. And for n, sorry, and for r there is a room for confusion, because if we just write r, then you do not know what is n. Okay, it could be 10 or 20, it could be k, or it could be some other integer. Anyway, so just please be careful about it. But whenever you are dealing with the dihedral group d2n, it is understood that r is this cos 2 pi over n and so on. Okay, yeah. Okay, this dihedral group forms an infinite collection of groups, and this is again one of the most important class of finite groups that we are learning. So we have learned this group mu n, we have learned the group z mod n z, we have and then we are learning this group d2n. And just one more thing, just let me have a quick look. I think I have discussed, yeah, that the subgroup of gl2r generated by r is isomorphic to mu n. Okay, yeah. And anyway, so we have been discussing about the dihedral group, but one can talk about the dihedral group only after solving this exercise. Okay, because this comes at the very end, at the third point. So we need to first show that these elements, I mean, no two elements are distinct. No two elements among this bunch of two elements are distinct, or rather, no two elements, no two elements of no two elements among these two elements are equal. I'm sorry. I had that they should be distinct in mind, but I ended up saying that no two of them are distinct. What I meant is that any two of them are distinct. In other words, no two of them are equal. So then this set d2n is of size 2n. There is no confusion about it, thanks to part 1. And then the second part says that d2n forms a subgroup of gl2r. Okay, let's see. We'll try to discuss a bit of all that today. Okay, great. uh, yeah, so let's recall that we have already learned this notion of an automorphism of a group. An automorphism of a group is by definition an isomorphism phi from G to G. So an isomorphism is a group homomorphism phi from G to G, or rather, okay, so you can certainly define from G to G, but let me just try to recall the general definition. An isomorphism from G1 to G2 is a group homomorphism phi from G1 to G2, such that there exists a map psi from G2 to G1 such that both the compositions are identity on the respective domains. Okay, this makes sense. Yeah, so just recall, go back to the definition if you think that you need to get back to there. Okay, great. So we are going to just deal with isomorphisms from G to G. In other words, automorphisms of the group G. Okay. So we'll start with the group. So you start with the group G, and let's pick an element little g, and then you define a map. Okay, which sends any given element h from G to GH G inverse. Okay. Maybe you are familiar with the map h going to GH. while we were dealing with cosets. I think we have studied this kind of maps in some implicit form, and also probably while establishing the Lagrange's theorem. Okay. Anyway, so we define this map psi g from G to G, which sends which sends H to G inverse for any H in G. And now this first part of this exercise says that says to prove or rather asks to prove that psi sub G is an automorphism of G. This map psi G has a specific name. This is called conjugation by G map. Okay, and again there you may get to see some other conventions in somewhere. Uh, so some so there are I think this is also in practice. And I mean, okay, I cannot say that we will not use it if you're using it. Sorry, yeah. So here, if you replace G by G inverse, you just end up getting this. But you see that. So when you so the map that you are considering puts G first and G inverse at the very end. But in certain references, or there are some people who follow this convention who first put G inverse and then put G. Let me just put another. Yeah, maybe that's much better. Another convention. Okay, so let me just not make any comment. Anyway, so this is another convention. Let's not just get into that. Let's try to understand the content of this exercise. So first exercise says that psi G is an automorphism. Okay, and now we collect all these automorphisms of G. Okay, we collect all these automorphisms psi G as G varies in G. Okay. Uh, yeah, then this forms a subgroup of odd G. Okay, this is what that you need to prove. This is called the group of inner automorphisms of G. Okay, and here is an exercise which says that the group of inner automorphisms of a group G is trivial. Okay, so recall that you have already defined this notion of a trivial group, or so a group is said to be trivial if it has got uh, okay, it's trivial. That means this has got order equal to 1. Okay, yeah. So this group of inner automorphisms of G is trivial. In other words, it has got order equal to 1 if and only if the group G is abelian, the group G that you have started with. Okay, the group G you have started with. And okay, just let me make a remark in the context of dihedral groups. This is quite trivial to see, but I mean, this is useful. Okay, as you see that this is already a conjugation. Okay, this is conjugation of R by the element S. So let me try to quickly give you a proof, or maybe I'll leave it to you, because the proof is really a one-line proof. So here we know that SR is 1, and just because we know that SR is 1, so okay, so let's just keep in mind that SR is 1. Okay, now where is the statement? Yeah, we know that SR is 1, that is same as saying SR S is R inverse, since S square is equal to S. This is same as saying that SRS inverse is R inverse. Okay, so this is not something new. Okay, this is just a variant of, or this is just a restatement of this equality. Okay, anyway, so now let me try to solve one of the exercises which was left for you. Okay, which was left for you. Let me try to do it on my own. Okay, let's try to discuss it together, or rather kind of let me put it in this lecture, and we can discuss it later on during the tutorials or during the office hours. Okay, so please feel free. Yeah, so to show that this D2n, as we claimed, forms a subgroup of GL2R, so I'm leaving exercise 1, or that is part 1 of exercise 157 for you. Okay, or maybe I will end up doing, I think, just give me a moment. So let me first show that no two elements among these are equal. So, and conclude that D2n is a group of order 2n. Okay, or rather, kind of, let me just okay, let me order things in a bit differently. Let's first discuss that all these elements are no two elements among them are equal. Okay, so So note that R power k is equal to this matrix. That can be proved using induction. Okay, this is not too difficult, so please work on it. So prove this equality. Okay, so it follows that this element R of GL2R is an element of order n. Okay, because you want this cos 2 pi k over n to be 1 and sine 2 pi k over n to be 0. Okay, that can only happen when k is a multiple of n. Okay, and that shows that the element R of GL2R is an element of order n. Okay, great. Sorry, it has just went past this this page. So we have these elements 1 r, r square, r cube, and all the way till r power n minus 1. They are all distinct. So you have got n distinct elements. And on the other hand, these elements are also distinct, because if any two of them are equal, so for instance, if SR is same as SR cube, then by left cancellation we can remove S from the left hand side. Okay, sorry, we can remove S from the left hand side to get that R is equal to R cube. Okay, and that will violate, or that will contradict the statement that these elements 1r, r squared till r to the power n minus 1, they are all distinct. Okay, yeah, I mean, I only considered the case when SR is equal to SR cube. This is just this is not a proof. Okay, this is just a way to somehow convince you that the statement is correct. Okay, but again, to see that the statement is correct, you need to go as follows. You need to, let me just use the yellow color. You need to say that suppose S times R raised to I is S times R raised to J with 0 less than or equal to I less than J less than or equal to n minus 1, and then after the left cancellation law and so on, and you end up getting that R power I is R power J, and then you conclude that this previous statement then you obtain a contradiction to the previous statement. Okay, and then that's not possible, so this hypothesis is incorrect. Okay, so do not compare something to explicit things when you are supposed to prove something general. Okay, so this is not allowed. Okay, so sometimes we of course do compare to explicit things or to explicit elements or to explicit numbers, but there is a step towards a final proof, or the final how to say finally what we are going to prove. Okay, these are steps towards the final thing, and as if you are able to if you're able to go through this step, then it means that we are all good, but for this step only. Okay, nothing beyond that. Sometimes we can see, but again it has to be stated precisely. And ideas are of course the guiding things in math, but once we have the ideas, we need to be able to work it out, and we need to be able to we should be able to state it explicitly. Okay, so now the claim is that so we are supposed to show that these elements are distinct. So we know that among the first n elements there is no repetition. Okay, all the elements are distinct, and the last n elements, they are also distinct. Okay, now to show that all these elements are distinct, we only need to show that no element from this first n elements is equal to no element from this list of this n elements. Okay, the second list of, or this list of n elements that lies to the right. So to show that none of these elements is equal to none among them. Okay, again the remaining elements SR power n just went past this slide. Okay, so I'll try to fix it in the PDF. So if that is not the case, if that is not the case, that means some element from here is equal to some other element from here. Then it will follow that S. Okay, so for example, okay, let me try to write it down. Oops, something went wrong. So if R power I is same as S times R power J, then it follows that S is R to the power something, right? Is R to the power I minus J. So it follows that S is a power of I. It follows that S is equal to a power of R, and then one can show that that is impossible, because the diagonal entries of any power of R, they are either 0 or they have the same sign. Okay, because you have got cosines. Okay, and whereas the diagonal elements of S are of opposite signs, so no two elements among so it follows that no element among this is equal to no element among them, and hence all these two elements that we have written here, they are all distinct. Okay, great. And now let's try to prove that this G2n is a subgroup of GL2R. Okay, how do you show that this is a subgroup? So let's first try to multiply elements, or maybe we take an element A and take an element B and try to see what happens with AB inverse. Okay. uh, yeah. So okay, so let me just try to show you what happens if you are interested in considering elements of the form AB inverse. Okay. Elements of GL2 are of the form AB inverse, where A and B come from D to N, because as of now we still do not know whether AB inverse lies inside D to N or not. Okay. So let's take an element A. You know, an element A of G to N is of this shape, is equal to either a power of R or S times the power of R. So it is S power I times R power J, where I is either 0 or 1 and J is an integer. One can say that J is between 0 up to N minus 1 or 1 up to N and so on. Okay. So we have got an element A, I mean, you've taken an element A and taken an element B, and you have expressed A as a product of a power of S and the power of R, and you have expressed B as a product of a power of S and a power of R. And now when you invert the second element, you end up getting R power L. Okay, I mean, sorry, R power minus L. And then these two elements can be combined by the associativity property, by the associativity property of the composition law of GL2R. Okay. So you end up getting R power, I mean, some power of R. And then the point is that, see, here you have got a power of R and here you have got a power of S. Suppose you can swap these two. Suppose, okay, this is not the case and this doesn't happen in general. Suppose you can somehow bring this power of S at the very beginning and push this power of R to the right, then you will be, I mean, you will be in a good shape, because in that case S power I can be combined with that power of S power, with the other power of S. What I'm saying is that, okay, what I am saying is that here you have got S power I is R power J minus L, and then S power minus K. Oh, I meant S power I, not R power I. Suppose S power minus K can be put first, then you can somehow combine these two, right? Then you can combine these two to get S to I minus K, R S to J minus L, and I mean, that looks good, because you're just trying to express any element of I mean, we know that any element of D to N can be expressed as S power I and then R power J in this form, right? Well, but the thing is that, just give me a moment, this does not work. Suppose, and then this does not work, okay, unfortunately or fortunately. That's why we have an example of a nice group anyway. So we have an example of a non-abelian group, or rather we have a family of a sequence of we have a family of non-abelian groups anyway. So what we are discussing, just somehow lost the track. Yeah, okay, we are here. Okay, so here we had a power of R times a power of S, and then we wanted to kind of swap the order, or rather, instead of getting S power minus K or maybe R power this, maybe we can swap. I mean, so here we have maybe R power star and S power double star, and somehow maybe we can make it S power dagger and then R power double dagger. Okay, so that would be great. Okay, even in that case, you can combine these two powers of S together. Okay, so let's try to do it. So we are trying to express R power J times S power I as some power of S times some power of J. That can be done. So here is a description, or here is an argument. So note that for any integers ij, if you have got R power J S power I, then you can put S power I and S power minus at the very beginning. Okay, and then what you have is S power I and then this, right? One can show that this is indeed equal to S power minus S power minus I and then R and then S power I whole raised to J. Okay, this can be obtained by induction. And and here if I is odd, then one can show that this is equal to this quantity or this element, and if I is even, then one can show that this is equal to this quantity. Okay, because if I is even, then S power I disappears, in the sense that this becomes identity, so it doesn't play any role while multiplying. And then if S power is identity, then these two elements also disappear. In other words, they become identity more precisely. So then you have just got R power J. So you have got R power J, and when I is odd, then of course you have S power I. And on the other hand, okay, well, So if I is odd, then s power I is just equal to s. Okay. So here what you have is s raised to minus 1 and then r and then s whole raised to j. So which can be just for simplicity and with no change, with practically no change at all, you know that this is s inverse whole raised to j, and you know that s inverse is same as r inverse. So then you are done, because then this becomes r inverse raised to j, and what we have here is r power minus j, right? Then you are done. Great. Okay, so we know that how to swap a power of how to interchange a power of r with the power of s. Okay, so r power j times s power I is same as is s power I times r power okay, not j, just minus 1 raised to j. Okay, great. And now, okay, one can do all this computation. So r power this times s power this is same as the power of s times r raised to the same integer multiplied by minus 1 raised to the exponent of s that we had here. Okay, so this becomes s raised to I minus k, and r raised to minus 1 raised to minus k times j minus l. Okay, in other words, we know that for any AB inside D2n, the element AB inverse of GL2R, this lies, it also lies inside D2n. Okay, and certainly D2n is non-empty. This contains this identity matrix. Okay, 1 0 1 1. So D2n is non-empty, and so it follows that D2n is a subgroup of GL2R. Okay, and then of course we know that D2n thus becomes a group of order 2n. Okay, and just now while discussing this dihedral group, we yeah, okay, so here we are speaking about the order of R. So let's try to solve an exercise that deals with orders of a bit more general elements. Okay, or at least a bit different context, but learn something new. So suppose you start with a finite cyclic group. Okay, sorry, suppose you start with a finite cyclic group of order n, and we pick a generator of G. So I hope I have already introduced this term generator. So I mean, if you have a finite cyclic group, then it is generated by some element G. Okay, then we can talk about its generator. Okay, and a finite cyclic group may have got more than one generator. For example, the Z mod nz can be generated by several elements. It can be generated by 1 bar. It can be generated by even n minus 1 bar. Okay, and 1 bar and n minus 1 bar, they are distinct, at least when n is greater or equal to 3. Okay, so then you get to see that a finite cyclic group may have more than one generator. So that's why you're saying that G be a generator instead of calling it the generator of G. Okay, so usually if you start with a finite cyclic group, then you're not in a position to talk about the generator. Okay, unless this group is of order 1 or something like that. Okay, anyway, so for any k inside Z, this exercise says that this G power k, or maybe I should add that, show that the order of G power k is equal to n divided by the GCD of n and k. Okay, yeah, so this is an interesting exercise, and we'll do so as an application of this, our knowledge of GCD, or of how to say, or of I mean our knowledge of GCD, and which comes from our knowledge of division algorithm. Anyway, so let's denote the order of G power k by m. Okay, so we know that G power k raised to m, which is G raised to km, that has to be equal to the identity element. Okay, here E denotes the identity element of G, and since G has order n, it follows that n divides km, right? Yeah, since G has order n, in other words, n is the least positive integer such that G power n is identity, so it follows that n divides km. This follows as a consequence of the division algorithm, if you want. Okay, I mean, it actually follows from the division algorithm. Yeah, so what do we have? So we have that n divides km. Okay, so we can divide both sides by an integer which divides this and which also divides this, right? So we divide it by the GCD of nk. So you know that n over GCD nk divides km over GCD nk, or you can also write it as k over GCD nk times m. Okay, and we know that this GCD nk is the greatest common divisor of nk. So these two integers, okay, they don't have anything in common, right? I mean, they do not have any non-trivial factor in common. So it follows that n over GCD n k divides the integer m. It follows that n over the GCD of n and k, it divides the integer m. So the order of g power k, in other words, which is m, okay, that is a multiple of n over nk. And if you raise g power k to the GCD of n over nk, you end up getting the identity element, because the g power k raised to this integer is g raised to the product of these two integers. Then n can be put inside, and then the rest is just k over GCD nk. And the point that you need to note is that this is an integer, okay? So g power n is e, and you're raising e to an integer, so you'll end up getting the identity element, okay? So we have established that m, that is the order of the element g power k, is a multiple of n over GCD nk, and g power k raised to this integer gives you identity. So it follows that the order of g power k is equal to n over GCD nk, as has been asked to show in this exercise, okay? Great. Let's try to see another application of division algorithm, which says that a subgroup of a cyclic group is cyclic, okay? So we start with a cyclic group. Okay, we have seen some such thing, at least some application of the division algorithm, where we were trying to classify, or when we are trying to classify all the subgroups of Z, right? We showed that all the subgroups of Z are of the form k times Z for some integer k greater or equal to 0, right? Okay, anyway, so yeah, so now we need to, now let's try to, okay, not classify, or rather try to prove a property of the subgroups of any cyclic group, okay? So you already know that the subgroups of Z, they are cyclic, because it is either 0 or maybe k times Z with k greater or equal to 1, and they're certainly cyclic because kz is generated by Z, is k, okay? Kz is generated by k. So you already know that a subgroup of a cyclic group is cyclic, or rather, only in the specific context of the group Z, okay? So when you have the group Z, then you know that any subgroup of that group Z is cyclic. But let's try to prove a more general statement which says that a subgroup of a cyclic group is cyclic, okay? So you start with a cyclic group G, and let's pick a generator G of G. Pick a generator little g of the group G, and we pick a subgroup H of G, and if H is a trivial subgroup, then H is of course denoted by the identity element, its only element, the only element of H, and then certainly the group H or the subgroup H is cyclic, right? Now it only remains to consider the case when H is non-trivial, okay? And in other words, when H contains more than one element, okay? So which we assume from now on. So we know that H contains some non-identity element, right? So, whoops, yeah, so H contains some non-identity element. So we know that, since H is a subset of G, and G consists of the parts of this element little g, since little g is a generator of the group G, so the elements of H are of the form G power n, okay? Any element of H of the form G is of the form G power n for some n, okay? So we know that H contains G power n for some non-zero integer n, right? And now, since H is a subgroup, it will also contain its inverse, okay? It will also contain G power minus n. So you know that for some non-zero integer n, okay, so you know that any element of H can be expressed as G power n, right? And some element of H can be expressed as G power n for some non-zero integer n. Because if all the elements of H are of the form G power n with n equal to 0, then H will just be trivial. And we are assuming that H is not trivial, okay? So H contains G power n for some non-zero integer n, okay? And since H is a subgroup, G power minus n also has to lie within H. So if see that for some non-zero integer n, G power n and G power minus n both are there. So it follows that H contains a positive power of G, okay? So it contains a positive power of G, and we pick the smallest such positive integer. More precisely, we pick the smallest positive integer I, such that G power I lies inside H. And now we'll apply division algorithm to conclude the proof, okay? So now we claim that H is generated by G power I, okay? So we pick an element, to show that we pick an element little h from H, and you know that G is generated by G and H lies in G, so you know that H is of the form G power K, and now we apply division algorithm to these integers K and I, so you end up getting a quotient and a remainder, okay, with all these properties. So and we And then it follows that h, which is g power k, that is g power this qi plus r, and this is g power I raised to q, and then g power r. And since h lies inside h and g power I, by the choice of I, g power I lies inside h, so these two are elements of h, so it follows that g power r is also an element of h. Okay, but r satisfies this criterion, and on the other hand I is the least positive integer such that g power I lies inside h, so r cannot be positive, so r has to be 0. In other words, h is g power I raised to q, so h is a power of g power I. Okay, so you have established that h is a power of g power I. Okay, in other words, we have established the claim that h is generated by g power I. So note that g power I lies inside h, so all the powers of g power I has to be contained inside h. So since h is a subgroup and gi, since h is a group and gi is contained inside h, it follows that the subgroup generated by g power I that is contained inside h. So we wanted to show that this is an equality. Okay, so for that we picked an element little h from h, and now we showed that little h is a power of g power I. So we have established that h is generated by g power I. So the proposition follows from this claim. Okay, which was that h is generated by g power I. In other words, h is cyclic. Okay, we have established when h is non-trivial and when h is trivial, that case has been dealt earlier. Okay, from the very simple observation that h is generated by the identity element. Okay, great. Now here is an exercise. Maybe this is something that I stated. Yeah, this is something that I think just stated a while ago. Yeah, that is n divides k. Okay. This is something just I have put here. Okay, as a very last topic of discussion. So I leave it to you to go through this exercise. Okay, this is an interesting one, and then you should try to have a look. Okay, so let me this is an interesting or rather very elementary application of the division algorithm, and very similar, similar to the our previous discussion. Okay, and this is something that you will or you may get to see very often being used over and over again, and some such thing has already been used while showing that while classifying all the subgroups of Z. Okay, so please make sure that you understand these solutions, not that you remember, but you understand. Okay, that you will be able to produce this argument whenever you are asked or whenever you require. Okay, so let me conclude this here.